And okay, we are now recording. So I will hand over the meeting to group 2 to show us your design.
All right,
Yep.
Gabe, you got it?
Yep, I'll share my screen right now. And play from beginning. Okay, can everybody see my screen, the presentation?
Yes.
Okay,
Okay.
excellent.
Okay, so our project, we've titled it the Semi-Autonomous Microbioreactor, which if you've ever seen Phineas and Ferb, that's a hilarious name. If you haven't, that's just what we're calling it. We're group 2. Go ahead to the next slide. So an overview of our project. Yeah, it's an overview of our project is this is our system. We have 7 subsystems. First one is liquid handling, which is located right on the nozzle of where the tubes are, and it's the tip which is going to distribute fluids throughout the rest of the system. There's a liquid control system, which is the entire top XYZ portion. I would be pointing it out to you, but I can't on the screen. But it's the entire XYZ portion. It's responsible for movement across along the rest of the bioreactor. The next one is the well tray movement subsystem, which is, you can see it inside of the lid, and that's what's responsible for shaking the plate in the orbital, double orbital, linear patterns. The chamber control subsystem, which is pretty simple, just on the left-hand side inside of the lid, there's a little pocket, and that's where you put the phase-changing wax that we're using for chamber control. It's responsible for controlling the temperature of the chamber. The chamber enclosure is our next subsystem, and that's just the overall, it's got gaskets, it's got the overall framework of the chamber. Note that the things that are transparent on it, the lid and the top, the 96 adapter, aren't actually transparent. I just made them that way so you could see through. The optical density and fluorescent intensity portion, so that is 2 steps to that. So on the top, moving along the XYZ, you can see that there's like a bunch of parts there. That would be the top half of the ODFI sensor, and there's also a bottom half to it because it needs to shine a light through and be able to read on both sides. So the top half is on the XYZ on the liquid control system, and the bottom half is on the inside of the chamber. There's slides on the bottom for it to be able to move, and basically they sync up and they can read each well individually. So we'll go more in depth in that later. The last system is the system interface, which isn't shown here. It's just an iPad on a stand, and the important part of that is more the interface than the actual object. And for space, we just didn't include it. But you'll see it later in the PowerPoint. The last section is the framework. Excuse me. The last section is the framework. It's not considered a subassembly. It's just all the external features that we needed to combine everything. So the turbidostats, the beakers, the aluminum rods, like the framework and the shelves and stuff. And we will get to questions at the end. So if you're good to go on to the next page. So our product overview. The semi-autonomous bioreactor we have designed has several stages. So the first stage is when the person's setting up the machine. So they place in the beakers, you're going to place their cells, or your media, whatever that is, the stressor that you're choosing to use, and cleaning fluid, and then taking one of the tubes and putting it in an empty bucket for waste. The machine fills the trays with cells and varying amounts of stressor, and then a person's responsible for closing the well chamber. So an important feature of our design is that a person does need to come and open and close the chamber whenever it needs to be changed. So if there needs to be media added or if there's data collected. So at the beginning and the end, the person needs to be there. In the experimental stage, the well tray is consistently shaken in any of those 3 patterns, whichever one you set it to, and enclosed in a chamber which can be set at a temperature between 4 degrees and 70 degrees Celsius. We don't have every degree in there, but we have most of them. And from what I've heard, about 2 degrees, within 2 degrees is accurate considering the rest of the projects in this course. A person is responsible for opening the lid to the well tray chamber, and an ODFI sensor observes the effects of the stressors on the cells. So during the experimental stage, at any point, the person can choose to pause the experiment and collect data, therefore opening the lid and running the ODFI sensor along to read the data inside the wells. The last stage is cell proliferation, where the cells are moved from the well tray into the turbidostats that were in the front right side of the bioreactor. And that's just where they're going to sit, proliferate, and then eventually be moved back into the wells for another round of experimentation when the person comes back and says, okay, I've done my 2-week experiment, let it proliferate for a little while, and now go back and do another experiment. And it'll store the data, repeat the experiment as many times. So our hedgehog concept, or overall, is that this bioreactor requires the least amount of technical knowledge of any on the market to operate safely and effectively. So it does require some human interference to open and close the lid mostly, but doesn't require any technical knowledge, and it's very easy to operate and relatively safe. So if we're good to go to the next slide.
So I'll be talking about the liquid handling subsystem, if you want to go to the next slide. So the purpose of the subsystem is to collect and dispense the various fluids between the beakers and the well trays. And it is a quite simple system. It only consists of 4 parts. The main component is a peristaltic pump. And so that pump requires a single tube to run through it. And then on one end, we have a tube tip, which is just a barbed fitting. And then that tip has a mount that the tube and the tip connect to, such that it can be mounted on the liquid control system that moves in the X, Y, and Z direction. And so the way that it works is peristaltic pumps only require 1 tube to run through it. And so one end of that tube will be suspended over a waste bin, and the other end will be attached to the tube tip and mount as I just described. And so as the pump rotates, it has rollers that will physically push fluid through the tube. And so the pump can both collect and dispense fluid, just depending on which direction the motor rotates. And so the flow rate depends on how fast the motor rotates, and the amount of fluid depends on how much the motor rotates. And so the first step is to collect fluid would be to submerge the tip in the desired fluid. And then it goes in the reverse direction to collect. The motor turns in the reverse direction to collect the fluid. The liquid control system navigates it to the X, Y, and Z location that you would want to dispense the fluid. Then the motor turns in the forward direction, pushes the fluid out of the tube, and that repeats until it's done handling one particular fluid. And so when you want to change to a new fluid to avoid cross-contamination, the tip would submerge in cleaning fluid, and the motor would run in the reverse direction until the line is completely flush. And then this process would be repeated until the liquid is completely handled. Next slide, please. Okay, so the customer needs that are specific to this subsystem address the dispense rate, the amount of volume dispensed, and the fact that it should be able to dispose and neutralize waste. And so as I described, all of these needs are met because the dispense rate just depends on how fast the motor turns, and I'll go into those specifications in a second. The amount of volume depends on how much it turns. I'll also go into those specifications. And as I described, it is able to flush the line with any cleaning fluid such as isopropyl alcohol or chlorine. And so here's a breakdown of the cost. It's only a total of around $80. It's a relatively inexpensive subsystem. And because it is a stepper motor with a relatively small degree per pulse, it is also accurate, and it's often, peristaltic pumps are often used in laboratory environments. And so even though the pump itself is fully operational, it's sold on the market already, I would give the pump a technology readiness of 9. A technology readiness level of 9, there we go. The combination of all these parts into this subsystem and the specific application and customer needs that we are addressing has not been verified in a laboratory environment. So I would give the overall subsystem a technology readiness level of 3 because it has been analytically verified, but not experimentally in a laboratory environment. Next slide. And so here's some more specifications on the pump. Like I said, it's 1.8 degrees per step on the stepper motor. It is self-priming. And then the tube that we're using is a 3/16 inner diameter, chemically resistant flexible tubing. Here's a chart provided by the manufacturer. And if you go to the next slide, it's a little bit more simplified. So here's showing the linear relationship between the flow rate and the motor speed. And as you can see, we meet the customer requirements of 300 microliters per second. And so variable flow rate and variable volume dispensing is very desirable for this particular application when you have various fluids and experiments that you would like to run. Next slide. Thank you.
I was muted. All right, liquid control subsystem. So this is the one that's responsible for the XYZ movement across to the bioreactor. Subsystem moves along the 3 axes using a belt and pulley system in a Cartesian configuration. The dimensions of the system allow for reaching into every possible receptacle. So that's the beakers, it's the well trays, and it is the turbidostats on the front. So the 2 customer needs that are addressed are 25 and 28. They basically say the same thing. One is for the wells and tubes, needs to be able to reach all of them, and the other one is saying that you need to be able to measure ODFI in all of the tubes. And since both the liquid handling system and the ODFI are attached to the bottom of this system, they're able to do so. Go ahead to the next slide. All right, so simple size analysis, just to make sure that we can reach all of the wells, is that the motor that's used to move the subsystem on the XY axis, or I guess on all 3 axes, is a NEMA 17 stepper motor. It moves in 1.8 degrees per step of the motor, and the axle diameter is 5 millimeters. So with the pulleys and the belts, able to move at a distance of with each turn or with each step of the motor, it's able to move about 0.07 millimeters, which allows us to reach all the wells. The diameter of the smallest well that we're going to use is on a 384 well plate, and that diameter is 3.5 millimeters. The well plates all pretty much come in the same dimensions. It's the wells that's change diameter, and since that's the smallest one, we will be able to reach it since we can move in such small increments. Another important thing to note is that our overall assembly, the range of this assembly is able to reach up to 41 inches long, 21 inches deep, and 10 inches down, so it can reach inside of all of those 3 receptacles that it needs to. Go to the next page. All right, strength analysis. This part was just done to ensure that the entire system isn't going to break due to the weight of it. So in the middle, moving across the x-axis, you can see there's that long one with the 2 sides on it, and that's so it can move across the xy axis. So what we did was we did a strength analysis, is calculate the weight of all the stuff in the middle, as if it's straight right in the middle of the z-axis, add all the weight to it and see how much it deforms. As you can see from the bottom right side, the deformation of that straight aluminum rod that has all the weight on it is about 2.5 by 10 to the negative 3rd millimeters, which means it's hardly going to deform and that it is strong enough to hold the rest of the subsystem. So good for the next page. Last thing to mention is the bottom ODFI movement. So like I said, we went with belt and pulleys for the rest of the subsystem because they are not very expensive. They work pretty well. They're not very expensive and they work pretty well. But for the bottom portion, we still have to move the ODFI sensor to match the top of the ODFI. And the way that we chose to do that was using lead screws. We didn't want to use the belt and pulley system. Particularly, the most important reason is because the chamber is going to heat up to 70 degrees Celsius. And the concern is that since the belt is elastic, it's a type of rubber as opposed to type of metal, that it would deform with the high temperatures inside of the chamber. So instead of using the belts, we use these lead screws, which they're powered by the same motors, so they can move along the same increments of about 0.07 millimeters, and can move easily and sync up with the top of the ODFI so they can easily measure properly. So then on the next slide, you can see the costs. A big portion of the costs do come from those bottom ODFI rails, but like I said, we didn't really want to switch it to pulleys because we're worried about the heat. The total cost of the subsystem with pulleys, belts, axles, there are limit switches throughout the entire thing on all of the XYZ motion. And then also there's another limit switch on the bottom of the Z axis. So that way if it accidentally runs into the lid, because we have the lid, right, that has to be opened and closed. So if the lid is closed and it runs into it, a limit switch is going to stop it from running and stop it from moving, send an alert or something, because we don't want to be going too far, running into the lid and breaking our system. So there's an extra one added there. And otherwise, that is our total cost is around $3,500. This is the most expensive subsystem. The rest of them are a lot less expensive as we move on. So, and our technology readiness level falls somewhere within technology readiness level 3, because we are verified on paper, but not in a laboratory setting. So that's where we're standing with this one.
The next subsystem that we'll be talking about is the well tray movement subsystem. So this subsystem is pretty self-explanatory. The purpose of this subsystem is to move the well tray from side to side and in different shaking patterns. The main purpose of movement in a microbioreactor is to increase the availability of nutrients and improve oxygen flow to the cell cultures. So the design that our team created involves the use of two linear actuators. One actuator will be pushing up against the side of the well tray on the x-axis, and another one will be pushing against the y-axis. The well tray will be sitting on a platform with enough displacement with springs on each opposite end, where as the actuator is pushing up against the well tray, it's able to have a 10 millimeter displacement. The two needs that are addressed in this subsystem are that it accommodates each of the following culture plate sizes: 6, 24, 48, 96, deep 96, and 384. Inside of the platform, there's a mold that is able to accommodate each of these culture plate sizes. And the customer required shaking patterns for this subsystem are in a linear shaking pattern, orbital shaking pattern, and double orbital shaking pattern. I'll explain how each of these three shaking patterns is achieved. But first, I'll show you a small clip of how this subsystem works. We have a DC motor which rotates a cam on a shaft. This cam will be pushing against a rod, which will compress and decompress the spring, pushing up against the well tray platform. I'll start at a pretty high RPM and then go down. And that's how the well tray movement actuates. So the shaking patterns, the way that we can achieve all three shaking patterns, linear motion is achieved just by the actuation of just one motor by itself. So either on the x-axis or y-axis, the well tray will be moving back and forth in a linear fashion. Orbital motion will be achieved when we have both motors actuating at the exact same time and at the exact same rate. That's illustrated here on this graph on the left. When we have equal displacements in the x and y axes, then it will form that orbital pattern, and also with the actuation forward and back. The double orbital motion is going to be achieved when we have one motor actuating at double the rate of the other at the same time. And both of the graph of a sinusoidal function is a good example of how this motor actually actuates. One of the big failure criteria that we had to analyze for the base plate is the vibrational analysis to see if there was any resonance. So we calculated the natural frequency of the base plate and calculated it to be 91.82 hertz. The maximum operating frequency of the well plate shaker is based on very common orbital shakers found in industry. Almost all of them had this maximum operating frequency of 40 hertz. I modeled the linear actuators based off of this maximum frequency. So since this 40 hertz is significantly lower than the natural frequency, resonance will not be an issue with this subsystem. Another source of vibrational failure can also be if the maximum input displacement is significantly high. The maximum input displacement of the actuators is only 10 millimeters. So it's so minute that it will not have a negative effect on the well tray, on the base plate. However, to be extra safe, we decided that we will install a dampener to diminish the energy and the vibration in the base plate, just to be extra safe. It'll be absorbing the vibration from the actuation. These are the costs of the subsystem. Most of the cost is actually going to be found in the OTS parts, which is, since there are two actuators, we're going to have two motor couplers, two position controlled DC motors, 2 compression springs. Raw material costs is for aluminum sheet metal, rectangular bar stock, round bar stock. Manufacturing costs, we will need the use of a mill, lathe, and sheet metal cutting skills, $53.08, and then assembly $30 to bring a total of $423.15 for this subsystem. The technology readiness level of this subsystem is 3 because it has been analytically verified, but it has not been verified in a laboratory setting. Thank you, and I'll move it on to Carlos.
Thank you, Gabe. Now for the chamber enclosure. Next slide, please. The main purpose for this subsystem was to create the ability for the microbioreactor to provide a controlled environment with the ideal conditions for cell cultivation, and then flexibility to change the environment depending on the lab application, in addition to the chamber controls. So as you can see here on the image on the right, the main components are the main chamber body, that 96 adapter that Jess mentioned earlier, and then the latches on the chamber lid over the well plate. So the main customer needs addressed by this subsystem are the capability to include the samples, incubate the samples for up to 2 weeks, which is addressed by the upcoming heat loss rate analysis, and facilitating a fully enclosed environment, which is addressed by the gasket, strain seal, and material analysis upcoming. Next slide, please. Here you can see the gasket analysis. After extensive research, we decided that the silicon rubber would be the best gasket material due to the listed material characteristics, such as good thermal stability, excellent resistance to ozone, sunlight, and oxygen, and then also consistent properties at high and low temperatures. In order to simulate this material's behavior, in ANSYS, Amuni-Rivlin 2 parameters for the elastometers available were applied to a similar gasket geometry. As you can see, the chamber lid applies a distributed load across the gasket that, in addition to the chamber latch that I mentioned earlier, will create a fully sealed environment. And as you can see on the ANSYS image on the right, everything is in blue, so there's no off balance of applied strain or stresses, and material characteristics under that image. Next slide, please. Here's the heat loss rate analysis that I mentioned earlier. And this is simply material specific. So for the chamber enclosure, we'll be using 316 stainless steel sheet metal. And again, this is not including the insulation that we will be applying to that chamber body. The resulting heat loss rate was a 0.238 joules per second. And then to apply the customer need of up to 2 weeks of incubation, we did apply that change in time, and a total of 288.41 joules would be lost in 2 weeks. Next slide, please. So here you can see the heat loss rate analysis with insulation. As you can imagine, the heat loss rate is much smaller. So here we have a 1.07 e to the negative 4 joules per second when compared to the much larger heat loss rate without insulation, and a much lower loss in 2 weeks of 121.86 joules. And again, all these variables you can see at the bottom left what they are. So net heat energy transfer, time taken, difference in temperature, and the insulation that was analyzed here was a polyurethane variation. Next slide, please. Here's a full cost breakdown for the chamber enclosure. So OTS includes rubber grommets, the gas canisters, and the air regulators. Raw material would be the 316 stainless steel sheet metal, which will be welded, and the polyurethane insulation of the adhesive variety. So we're able to have a good seal and stick within the chamber body. And then manufacturing and assembly with a total of around $1,600. And then for the technology readiness level, due to the extensive analyses that we have on paper, the best level would be level 3, but it has not been proven in a laboratory setting. So level 3 seems like the ideal spot for the chamber enclosure subsystem.
Okay, so the chamber control subsystem, the purpose of this subsystem is to temperature control for the chamber enclosure. This includes 40 phase change materials, also known as PCMs, the polyurethane foam insulation sheets, and a PCM holder that all are necessary to keep the chamber at a stable temperature. So the two customer needs addressed are requirement 18 and 20, the capability of incubation and hibernation periods from 1 hour to 2 weeks, and the ability to go from 4 degrees Celsius and 70 degrees Celsius. Next slide, please. So the phase change material setup, we want to take advantage of the constant temperature these phase change materials hold while melting or solidifying. The oils and fats that these properties hold will stay in that phase and remain a certain temperature until the phase change process is complete. So the way it's done is you choose the desired temperature for your experiment, then you place the PCM of that temperature inside a laboratory refrigerator or oven, depending if it is above or below ambient temperature. After the liquid handling system has filled the wells, place the PCM in the wax cup and close the chamber lid. Go ahead, Ian. So phase changing material properties. These are substances that absorb and release thermal energy during the process of melting and freezing. We get our PCMs from Pure Temp. They can heat or cool from temperatures between -40 degrees Celsius and 150 degrees Celsius, which satisfies requirement number 20. So some of the advantages that they have, the heat energy storage capacities average 200 joules per gram. They're consistent, repeatable performance over thousands of melting and solidifying cycles. They're readily biodegradable, 100% renewable, and non-toxic. They store 5 to 14 times more heat per unit volume than materials such as water, and they're relatively accurate. They can store heat within a 2 degrees Celsius range. And on the left, you'll see the PCM in its liquid stage and in its solid phase. And then the chart shows the list of heat storage capacities and peak melting points. Go ahead. The energy required to change energy required to change chamber temperature from ambient to 70 degrees Celsius. So the delta would be 50 degrees Celsius, and here you'll see that it requires 13,236 joules, plus the 121.86 joules needed to maintain that temperature that Carlos mentioned, which results about 13,357 joules. If we divide that by the heat storage, the amount of heat storage it can hold, we result in about 0.15 pounds of PCM. And since we are using about 40 different temperature ranges, we can, and it costs $20 per pound, the total will come out to about $117. Go ahead, Gabe. So the cost breakdown for the chamber control cost, most of the cost comes from the phase changing material. Some of the other costs includes raw material for the sheet metal to hold the PCM, and the manufacturing welding $19 per hour for 30 minutes. I gave this chamber control TRL of level 7. It has been extensively tested through system demonstrations and practical use. One example of current usage includes maintaining goods at the desired temperatures while being kept in shipping containers. Thank you.
All right, so the optical density and fluorescent intensity measurement plays a pivotal role in the functioning of this autonomous microbioreactor. However, having vertical measuring systems provide a lot of challenges for us. So an overview is the optical density and fluorescent intensity acts as proxies for culture control and culture health. And we can take those measurements to constantly monitor and create that closed loop control that allows us to either increase the amount of media that's input into the cells or any other types of controls that we need to do. And so we're using a OTS optical sensing device, which is an open source microplate reader. And if you go into the next page, what is complex about it is that what's simple about it is that on the optical density side, a light is shined through with a given intensity, and it's coupled through a collimating lens, and then goes through the culture and then the well tray, and then it's received on the bottom side through a collimating aspheric lens, which is then received by a CCD visible range detector, which is capable of full spectrum and monochromatic attention. But on the fluorescent intensity side, we had to minimize that the amount of light that it's detected through our excitation sources, which can be LEDs for anything from 470, 525, 610, or any type of excitation frequency. And so with this configuration, we're able to exclude all of that light because of the collimating lens, the aspheric lens acceptance angle, and our narrow solid angle LEDs. And so you go to the next page. This is kind of an explorative view of the vertical train, the bottom and top assembly. And on the left side of the top assembly, you can see where the liquid handling goes. And then on the right is just where it overall sits in the assembly itself. Next. And here's a calculation of the customer number 30, where we need to meet a certain intensity level. And so through the excitation frequency, we're able to determine that we have a 25.06 kilowatt per centimeter squared intensity, which is well above the specified intensity of 1 kilowatt per centimeter squared. And the general cost, the most expensive part was an off-the-shelf CCD detector, and the total cost would be about $1,500. And the TRL for this subsystem would be somewhere on somewhere around 4, since it has been tested by other people, but we haven't tested it itself, and we're basing our information over someone else's kind of testing. That's it. Next. Yeah.
So the final system is the system interface. I'm going to go through this one quickly just for the sake of time. So the system interface is the means by which the user interacts with the machine and controls the necessary components and parameters. The system interface we chose is an iPad, as it's a readily available OTS part that can complete all of the desired customer needs. The needs addressed are shown here on the screen, but I'll talk to how it addresses them on the following slide. So if you go to the next slide, you could see that this is the example design of our system interface. So just starting from the top left, there is a system power button, which acts as the overall on-off. To the top right, there's an alert center, that shows the system alerts and kind of informs the user of anything that needs to be done. Directly below that, there's a progress bar that shows the experiment progress as well as the time elapsed. And then it also shows little tick marks for each time the experiment was paused for data collection. Then on the bottom is all the buttons that will take you to various screens. So on the bottom left, we have buttons that allow the user to input the experimental setup parameters, such as which well tray and type of well tray is used, the beakers and the contents of them, input shaking patterns, and control the chemical makeup of the chamber. In the middle, you have buttons that allow the user to see all the necessary data for each of the different systems. And on the right, the user can control all the different stages of the experiment. Again, for the sake of time, I won't go too in depth into all of them, but if there are questions, we can come back to those. And then here's the cost breakdown of this subsystem. Since it's using OTS parts, the main costs come from those, the iPad and the iPad stand, which can both be bought online or in stores. And then since there's no assembly or manufacturing time, the OTS parts are the total cost of the system. The TRL level given for the system was a score of 5 because the iPad has been extensively tested before being brought to market. However, it is not, the software for this specific purpose has not been tested in the lab environment.
Great. Last thing is the framework. It's just the rest of this frame includes the aluminum extrusions, the cell shelves, the turbidostats. I guess the most important thing is the turbidostats. We have 16 of them, so that when you're done running the experimental portion, you then choose the 16 best wells that you want to use, and it distributes the liquid into those turbidostats to run a lot of different trials in case one trial doesn't work out. So you have a bunch of different ones. And if you go to the next page, I think that was the end of our slide. So we're ready for questions. Do we have any questions today?
Are there questions?
Oh boy.
I'm sure of it. Actually, Andrew, I see your smiling face in here for the first time today. Would you like to have the first jab, as is tradition?
Andrew, are you one of our customers or one of our professors?
He is with Cummins.
Yes, indeed. And I have my ship barbecue background here from the ship barbecue last time we, before the pandemic. So just to kind of feel at home. Okay, so could I see, I'm sorry, I was a little bit late joining. I had a meeting before this, kind of ran over. So could I just see a picture of the overall?
Yeah, Gabe, if you want to go back to one of the first slides. I believe it's slide number 2.
Okay.
Hang on.
While he's doing that, just generally, you know, I think very good content and a good mixture, a good balance of, you know, technical depth in terms of equations and things. So that was good to see, and good kind of detailed pictures and things. The data you presented, I was pleased to see everything was labeled, and even like the FEA, although some of it was quite small to read, but you know, all too often there's kind of missing information. So and that was not the case here. There was good you know, good information on all the slides and complete with units and everything else. That was good to see.
Thank you.
What I would say, yeah, what I would say was, I mean, even though I missed this slide here, unfortunately, so for everything I sat through, you know, I wasn't quite sure in relation where everything was on the device. But even still, you know, don't forget that when you work on these projects as a team, that you become very familiar with it. But when you present it to somebody for the first time, of course, they'll take one look at this, and then partway through they'll be trying to remember where they saw the subsystem that you're talking about. So it's sometimes good to kind of show, as you go into each subsystem, not just an overview picture of the subsystem, but also maybe kind of referring back to this picture with the subsystem highlighted or something like that, and then that just helps you know, to kind of remember how everything's connected. I had a couple of questions. There was the shaker device or whatever it was called. It had like a cam on a motor. Can we go to that slide maybe? And there's a nice video, which is always good to see as well, so it kind of understands the constants. Yeah, there we go. So I would have liked to have seen maybe a little bit more about just how the cam and rod interaction is. Is there something on the end of the rod which helps it traverse around the cam? The cam seems very perpendicular to the rod. So I'm sorry, very kind of almost parallel to the rod in places. So as far as the rod moving up, particularly up some of the surfaces, you know, maybe not so much down, but you know, we use cams in our engines, and you know, you want to try and maintain contact. So and also you want to avoid you want the rod to slide nicely up the cam. When I mean up, I mean it's kind of difficult to explain without pointing at things, but
So maybe like a channel or something for the rod to sit in as the cam is rotating, like around the outside of it.
Well, no, it's not so much that. It's more the angle of attack. So you know, if this, for example, if this cam was a perfect circle, you know, if you imagine a wheel with the rod, then that's your ideal in terms of contact. It doesn't necessarily provide the movement that you need, but the ideal is a circle where the rod as you turn the circle, the rod smoothly glides along the surface of the circle, the outer edge of the circle. And then as you camify that, right, as you make it into a cam, the worst thing is almost what you see here, which is kind of a, almost like a long, thin cam where as it turns, the end of that rod is gonna struggle to glide nicely along that surface. It's got a lot of side load, right? So that side load transfers to heavy amounts of friction. And then as it goes down the other side of the cam, it can lose contact because the cam surface is moving away from the rod faster than the rod is descending on the cam. And so it's good to talk when you have a cam like this. It's good to show like a cam profile in like a diagram, and then talk about how you're going to maintain that contact, but also how you're going to minimize the contact stresses as you maintain contact. So that's always kind of the balance that you want to try and achieve.
Got it. I'm writing that down.
I tried to focus very hard on constricting the rod to only moving in one line of direction, but I do see that the path is not completely the path is not certain just with that constraint. I also needed to have had that maybe some sort of bearing path or something that it would follow to ensure that motion around the cam as well.
Yeah, well, I don't know it's so much that, but it's just, that if you look at the shape of that cam, it's very much like a squashed oval, right? I mean, it's shaped like this, right? I mean, it's not almost circular. It's like this. So as as it turns and the rod's trying to go up like this, up that surface like that, you can imagine there's a lot of side load there, and it can stick as it tries to work its way, along that surface. So yeah, it's just thinking about, would you need like a small, like a ball bearing or a wheel on the end of the rod, which helps it move more smoothly? Or is there a way to change the profile of that cam and do something else where you still get the movement that you want, but while minimizing some of those issues with the cam shape? It's a very shape.
My guess, the way this is set up now, as soon as you turn that motor on, that it would just shred that spring thing. It would just blend it. Doesn't look like there would be as forgiving as it shows in the video. But the thought was there. It looks good, but like Andy said, just maybe a little bit more thought into that cam shape.
Increase that width, decrease that length a little bit.
Something, yeah.
Closer to a circular pear shape.
We'll look into also the ball bearings. That's what kind of stuck in my mind when you said it. Just like at the tip of that. We'll definitely look into that.
Thank you for the feedback.
Oh yeah. So that. Oh.
Tom, I'm going to write that down too. Thank you. Any other points that we want to talk about? I know we're running low on time, and I want to make sure we get through everything.
That's right. No, I'll give other people a chance. But thanks for.
I was just going to comment that Tom had two kind of points he commented on. He mentioned at the beginning that he wasn't able to get his phone to connect on audio, but he mentioned the mechanism to generate linear motion seems like it would have a lot of transverse force. I'm not sure which assembly that was. I think it was on this slide. Oh, he did? Oh, that guy. Gotcha. Okay, cool. Cool.
Okay.
Sure. And then you said something about not using pulleys because of heat, and that really confused me.
So that's inside of the chamber. On the outside of the chamber here, we're using pulleys, but inside of the chamber, it's going to be a closed chamber where it's airtight. And I mean, the goal is to make it 70 degrees Celsius. And the concern is that it will get too hot and the belts will no longer remain as elastic as they were, or they'll stretch or whatever the issue is. And they won't, since they're made of a type of rubber, since they're elastic, they will deform and then not be able to move as accurately because the top and the bottom of the ODFI have to line up pretty precisely. That's the concern.
Okay. How much would they? How much would the temperature affect it? It's only 70 C. How good is the rubber in the belts good up to? A lot of you can also get belts for those pulleys that are Kevlar reinforced. Like you said, we didn't want to use it because we're worried about this.
Mm-hmm.
Prove it.
Okay. Well, dude, I don't know off the top of my head. I just know that that was a concern that we had, so we just decided to switch it over. But it is a huge detriment to our costs, and we've been noticing that. So I would look into probably.
And that's part of why I brought it up. Is it was the one thing that you mentioned was a significant cost, and I'm like, until you can prove that you shouldn't do something, assume you should.
Got it. Okay, we'll go back to that and see if we can switch it over. Another concern was the space, because the belts take up a little bit more space than the lead screw does, but there is probably a way to maneuver it so that way it takes up less space and it's able to fit within the chamber and still be able to move easily, so we'll look into that. Thank you, both of you, for bringing that up, Mimi and Tom. Thank you.
Okay, so there are a few more questions, but we're about 5 minutes over because we need to stop at 4 and move on to the next one. So maybe let's see. How do you align linear rails during this? So maybe if you guys could just address this last question that Ryan dropped into the chat, or maybe you did and I missed it, but he's asking, how do you align the linear rails during assembly to ensure they are parallel?
How do we align the linear rails during assembly? Let's see.
Does he mean on the Y movement on the liquid control subsystem, or on all of them in general? Because I can see how it could be a problem given that we have a pretty rigid assembly in the, let's call it, head of our system. And the way to potentially minimize misalignment errors could be to have close fit attachments, whether that is, we're using 1/4-20 screws. And so with a close fit, we're able to make those holes in a line and ensure that kind of it moves smoothly throughout the assembly.
Yeah, just my big concern was that if the rails are in any way not perfectly parallel to each other, you're going to run into issues with the gantry essentially binding itself as it moves up and down. So yeah, maybe some dowel pins for assembly so that you should get them perfectly in line. But yeah, that was just my big thing.
Yep, that would make sense.
All right.
My thought would be that since those could be the rails, which is what they're mounted on, could be mounted before the assembly is welded together, putting them close together and using something like a parallel, like we use in DML, to line them up and make sure that they're parallel to each other, and just moving it along to make sure that it attaches properly, like along the length of the thing. So that would be probably the best thought we got.
Well, thank you guys. I don't keep everyone too much over time. Dr. Trum, do you have any last words?
No, I'm good, and yeah, we are a little bit over, so we got to wrap it up there. So let me stop recording.